So we're in Chapter 4, Section 1, kind of backtracking from where we were. This chapter is on solving systems of equations with various methods. So you may, well you will tonight, you're going to see several different methods for solving systems of equations. You're going to see the graphical method, then you're going to see two algebraic methods called substitution and elimination, and then we'll be finished with this chapter. So we just have to cover three sections in this chapter, and they go pretty fast. The first method that we're going to, well, before we discuss that, we're going to talk about what a system of equations is. So if you'll look, a system of equations is when you have two equations that are called a system. I don't really know how else to say it, but they work together and they have a common solution. Usually there's just one solution, and that solution is the ordered pair at which they intersect. However, there can be more than one solution, depending on what type of equation you're graphing. So if you were graphing a curve and then a line, which I don't think we do that in this class, but if we did, then that line might intersect that curve in two places instead of just one. So it would have two solutions. If you are graphing a line and then another line, and they happen to lay on top of each other, then that means that they share every point. So they have infinitely many solutions because you have infinitely many points on a line. It is also possible that two lines might run parallel to each other, and if that's the case, then they have no solution, okay, because they don't have a common point. So again, you're going to be looking for the common point that they have. Now, the first thing that we're going to do is just kind of look at a system and decide if a ordered pair that they give us is a solution to this system. So this is example, well, it's not an example, it's the first one there on the page, and your system is x plus y equals 4, and I'm going to write them beside each other instead of one above the other, because this is how I like to spread out my work so I can show all my work. So the next part of the system is 2x minus y equals 5. And they ask us, is 3, 1 a solution? You need to recognize the ordered pair as x, y, okay? X is the first term or the first coordinate of the ordered pair, and y is the second coordinate. And then what you're going to do is you're going to plug that ordered pair into each equation. And if you get a true statement on both of them, then the answer is yes, it's a solution. If you get a true statement only on one but a false one on the other, then it's not a solution to the system. It's just a solution to one of the equations, so you just say no, it's not a solution to the system. So these two equations together are the system, and this is a possible solution to it. So I'm going to put 3 in for x plus 1 in for y. Does that equal 4? And I usually like to put a question mark over my equal sign. 3 plus 1 is what? 4. And 4 does equal 4. Now, you can't say yes, it's a solution until you show that it works for the other one. Okay, so you're going to do the same thing. 2 times 3 minus 1, does that equal 5? 2 times 3 is 6. 6 minus 1, does that equal 5? Yes. 5 equals 5. So the answer is yes, 3, 1 is a solution, and I'm going to abbreviate that SOLN, to the system of equations. Now what I want to do is I want to pull up a piece of graph paper, and there used to be some saved on this machine, but I don't think there is anymore. Okay, and I'm going to just paste it over here. And I'm going to talk to you about how to solve a system by graphing. Okay, so let's go back up to this one that we looked at. If we were to graph these two equations using what we know about how to graph lines, which that should all be pretty fresh in your brain, but I'll review it as we do it. But if we were to do that, then they would intersect in the point 3, 1. Okay, so they would intersect 3, 1 right there. Now, that is what we're going to do. We're going to go the opposite way. We're going to graph two lines and find their point of intersection. Everybody good with that? Do we remember how to graph a line? Solve the system by graphing. Two x plus y equals 1. And y equals x minus 2. Now, I like to graph by putting my equation in slope-intercept form. This one is in slope-intercept form, so as a review for you, slope-intercept form is y equals mx plus b. Where m is the slope and b is the y-intercept. So the slope of this line is 1. Remember, slope is rise over run. So you might make a note of that if that's been a while for you. So in other words, if it's not in a fraction, you need to put it in a fraction. You need to put it over 1. Okay? The y-intercept of this line, the b, is negative 2. So I will graph this one in red, since I've done all the work in red. We start by placing a dot on negative 2 on the y-axis. Now remember, this is your y-axis. Your x-axis is this one that goes horizontal. Okay. So I'm going to place a dot on negative 2, and I'm going to go up 1 over 1. That's rise over run. Rise 1, run 1. You can do it as many times as you want to. Now, it's super important that when you're doing this, that you get the line to go through the points well. And mine is a teeny tiny bit above the points. So that could cause me some issues in a minute. I'll just have to kind of see if it does. I think I'll be able to see where it's going to intersect the next line.
Where did you get the 1? See the -2.
Okay, right here. The number in front of the x is m. Hold on, let me get my pen. Your m is the number that's in front of your x. There is no number in front of my x here, so it's a 1. Okay? All right, is there another question before we move on to the next one? All right. So this one is not in slope-intercept form, so I'm going to manipulate it and get it in slope-intercept form. The y has a 2x added to it, so I need to subtract 2x from both sides. And when I do that, I will get positive y, which is just y, equals. Now, you can write 1 minus 2x, but according to slope-intercept form, it's better if it's written the x part first and the constant second, right? Because you want it to be mx plus b, like right here. So I'm going to write negative 2x, and then the 1 is positive, so I'm going to write plus 1. 1 minus 2x is the same thing as negative 2x plus 1. All right, what is the slope of this line? Negative 2, and we need to put it over what? To have a run, you need to put it over 1. And then the b is 1. So I'm going to intercept the y-axis at the number positive 1, which would be here. And my slope on this line is negative 2 over positive 1. So that means you go down 2 to the right 1, down 2 to the right 1. Now luckily, I already saw the point of intersection, didn't I? That up. Snap that line through it there. And yes, you should put arrows on the ends, but my thing doesn't give me arrowed lines. So I guess I can do this. You know they're there. If I don't put them, they're there. What is the solution to this system? It is this point of intersection. What is that point of intersection? Right 1, down 1 is the ordered pair 1, negative 1. So the solution is 1, negative 1 as an ordered pair. Now, if you have other methods of graphing that you like, some people like to graph by finding the x-intercept and the y-intercept. You're welcome to do that. I'm not going to review that one with you. This one is sufficient for the problems that we're going to be doing. So just getting it in slope-intercept form. Remember, m is your slope. B is your y-intercept. So you place a dot on your B, and then you rise and run your slope. If the slope is negative, then the line will fall from left to right. If it's positive, it will rise from left to right. Anybody ever built a house or been around a house being built, and you've heard them talk about the pitch of the roof being 8-12, 12-12, that sort of thing? And the steeper the pitch, the more expensive the house was. That's because it's harder to climb for roofers, and they have to put the toe boards down and stuff. So this is the same thing. It's slope. They're talking about the slope of the line that the roof makes. How many feet does it rise over how many feet does it run? So, all right. Let's do another one. Let's do one in which they don't intersect each other. So I've already told you what's going to happen. Get my graph paper over here. Okay. We are going to graph. Well, I'll tell you what, before we do that, let's look at one that looks like this, because I don't want you to be confused on it. 5x equals negative 10, and negative x plus 2y equals 2. I always write mine beside each other because I like to have room to work underneath each one of them. Now, neither one of these are in slope-intercept form. Do you notice something about this first equation? There's no y in it. So if there's only one variable in the equation, then you're either looking at a horizontal line or a vertical line, and you have to know which one it is. If the variable that is in the equation is x, then that line is going to cross the x-axis. In order to cross the x-axis, the line must be vertical. Okay? Now that's confusing to students because the x-axis runs horizontal. But a line that only has an x in it is a vertical line. And I'll show you why in just a minute. Let's solve this for x. So I'm going to divide by 5 on both sides. And I get x equals negative 2. This is a line. And like I said, it's a vertical line. It's going to be the line that's going to go through negative 2 on the x-axis. I'm trying to find some tool that's going to look better. I wish this wasn't dashed. Okay. I'll pick up my red pen. So I'm going to color this back in a little bit. So this is the line x equals negative 2. okay? Why is that the line x equals negative 2? Well, if you look at the points on this line, what is the x-coordinate of every point on the line? Negative 2. That's what that means. A line whose x values are all negative 2. This is negative 2, 1, negative 2, 2, negative 2, comma, 2.5. You see? Every point on this line has an x value of negative 2. Now, let's do this one. We're going to solve it for y. So I'm going to add x to both sides. 2y equals, I'm going to write the x first, x plus 2. Divide everything by 2. Now when you divide an equation, you have to divide every term. Terms are things that are separated by plus and minus signs. So you want to make sure and put the 2 underneath both of those terms on the right side. Y equals, what is the number in front of the x? 1. So I could actually pull this 1 over 2 out front and put my x in the middle. So it's 1/2 times x. That's what x over 2 is the same thing as. Plus 1. Now I can graph that line. I'm going to use a different color to do so. I'll do this one in blue. So I'm going to put a dot on positive 1. And I'm going to go rise over run. The top number is rise, the bottom number is run. So I'm going to go up 1 to the right 2. But it's carrying me away from my line, isn't it? I want to see where they intersect. So I need to go down 1 to the left 2, because that's the same thing as up and to the right. Down and to the left is a negative over a negative, and a negative over a negative is really a positive. So that's the same thing. And then you would draw your line through it, and I'm going to attempt to freehand it. Not very well, of course. And so my point of intersection is right there, and it is the ordered pair, what? Negative 2, 0. That's the solution to this system of equations that I started with. So graphically speaking, a solution to a system is the ordered pair in which they intersect each other. Okay? Sometimes lines don't intersect each other. So does anybody remember what's special about parallel lines? This will be going way back for you. They don't touch, okay? They have something in common. In order for two lines to not touch, let's say they look like this. That means they would have to rise and run at the same pace, wouldn't they? Very good. That was the word I was looking for. They have to have the same slope. So their slopes will be equivalent to each other. When you are setting this up to graph two lines, and you happen to notice that their slopes are the same, you are going to know immediately that they are parallel, okay? When you determine that they are parallel, then your mind is going to know immediately they can never intersect each other, therefore they have no solution, okay? And so that's what we're going to look at now. This is example 2 on page, well, I don't know what page it is in your book. X plus y equals 3. And 2x plus 2y equals negative 4. So what you want to do is you want to solve each of them for y so that we can graph them. I'm going to subtract y from both sides, subtract x from both sides. I don't want to move the y. I like where it's at. I get positive y equals negative x plus 3. So for this one, my y-intercept is at positive 3. And what's my slope? Interesting slope here. What is it? Negative 1? over 1. So if there's no denominator, you put it over 1 because every number is over 1 if it's not over something, right? Okay? See the negative in front of the x? That's your m. So how would I move from the y-intercept of 3, negative 1 slope? Rise over run. Negative means down, positive means up, negative means left, positive means right. So I'm going to move down 1, which way? To the right 1. Remember, this is a negative sloping line, so it will fall from left to right. Okay? Down 1 to the right 1. I could have moved. It's perfectly legal for me to say, well, maybe I want to move up 1 to the left 1 from my y-intercept. Up 1 to the left 1. Doesn't that put me in the same line? So that's fine. You can switch them up so long as you switch both of them up. Okay? So then I'm going to connect it with this. I'm going to try this one this time. You can use your imagination if that looks perfectly like a normal line. And we will go on to the next one. I'll do it in a different color. So we need to solve this one for y. What would I do first to get the y term by itself? Subtract 2x. Because it's positive and it's being added over here to something. So I'm going to get 2y equals negative 2x minus 4. You're going to divide everything by 2. Y equals, negative 2 over 2 is negative 1, so negative x, and then 4 over 2 is negative 2. So my slope here is also negative 1 over 1, and my y-intercept is negative 2. The b is whatever this is. If it's positive, it's positive. If it's negative, it's negative. So you're going to put a dot down on negative 2 on the y-axis, and you're going to have the same slope. Down 1 to the right 1, or up 1 to the left 1, whichever one makes you happy. And what we notice, please don't draw your lines with markers, but you can see they are parallel to each other, which you actually knew that to begin with because you saw that they got the same m's, right? Slope was negative 1, slope was negative 1. So they had the same m's, therefore they were parallel to each other. But your computer program is going to make you graph them even if you already know they're parallel, I'm pretty sure. Okay? Sometimes the lines end up being the same line. That's always interesting. You do not have to graph it twice if it's the same line. I wanted to move it, but it's not letting me pick it up. That's okay. So let's look at one like that. X plus y equals 2, and 3x plus 3y equals 6. So solving this one for y, we would just simply subtract the x from both sides. And I'm going to get y equals negative x plus 2, because the 2 is positive and the x is negative. Here, I would subtract the 3x from both sides. 3y equals negative 3x plus 6. We're going to divide everything by 3 to get the y isolated, and negative 3 over 3 is negative 1x plus 2. At this point, you should notice they are the same, which means when you go over here to graph it, you only need to graph it one time. Let's go back to the parallel one for a minute. When they're parallel, what did we say they have? What kind of solutions? No solution. Your book, let's see how they want you to do that. Does anybody know at this point how your book wants you to note, or how your computer program wants you to notate that? I think it's the empty set. I think this is what they want you to type in for no solution. Well, down here, because these two lines are the same line, that means that they are not like parallel lines who don't have anything in common. They have what in common? Everything in common. And a line contains infinitely many points, so when these two lines coincide, they both contain infinitely many solutions then. Okay? So it would be down one to the right one. So this would be my line. Again, freehanding, sorry for the sloppiness. And then that would be the same line, would lay on top of it. So it has infinitely many solutions. The way your book, now I'm going to write out the words, I'm going to abbreviate infinitely many. Infinitely many ordered pair solutions. Your book notates this very differently. They say the set of all x, y, such that, and then what they do is they write the equation of one of the lines. Nothing in here tells me if it's the same, if it matters which one. I'm just going to write this. I think it will accept it. So this means the set of all ordered pairs x, y, such that y equals negative x plus 2. That bar is the word such that in mathematics. Infinitely many solutions is what most textbooks say. Okay? Now, I don't know what page, but what page is that? Right there, what you're looking at. 145. On page 145, where it says review and complete, in that chart, is there a chart that outlines parallel lines and intersecting lines and all that for you there? Okay. That is important that you understand that chart, which is everything I've just talked you through. So intersecting lines have one unique solution. It is called a consistent system, and the equations are independent of each other. Parallel lines have no solution. They are called an inconsistent system, and the equations are independent of each other. Coinciding lines, meaning that they lay on top of each other, they're the same line, have infinitely many solutions. They are called a consistent system, but they are dependent equations because they're the same equation, so they depend on each other. Okay? Those are just some vocab words that you're going to want to familiarize yourself with. All right, any questions? Okay, we are going to move into the next lesson. There's tons of examples in here for you to look at. I don't feel like we need to just continue to graph and graph and graph and graph, but do take a moment to look over some more if you need to catch up on your graphing. I hope that's fresh on most of your brains at this point, or at least now that I've jogged it. But we're going to move on to section 4.2, which is solving systems of equations by substitution. Okay. What we learned up here was how to solve a system of equations by graphing. Okay? We learned also what it meant to find a solution to a system. It meant to look for an ordered pair that they have in common. Now we're going to talk about how to do this algebraically. Algebraically is preferred most of the time, so if somebody gives you a problem to work or you have a problem on a test to work and they don't tell you specifically which way to work it, you should go with one of the next two algebraic methods that I'm going to teach you, because graphical solving methods is not always reliable. All lines don't intersect in integer points. So who's to say it's not going to intersect at 1.7259 for the x-coordinate and 2.3247 for the y-coordinate. That would lie somewhere in the middle of one of those little squares, and you wouldn't really be able to tell exactly where the intersection was. So that's why graphing is just not reliable. We only do it primarily to teach you what a solution is, that a solution is an ordered pair that makes them both true, and it is something that you can see on a graph, but it's not always reliable. Okay? So substitution is the method we're going to do now. Now, what does it mean to substitute? Somebody put something in place of it. That's right. Replace something with something that is equal, right? So you, if you needed to call in sick, well, me. When I don't go to work, I have to have a substitute teacher. So I have to have someone who can come in and check roll and keep the kids in their seats and don't let them kill each other, right? Okay? Same thing here. I need something of equivalent measure to substitute in for one of the variables so that I can solve this system without graphing it. So look at this first example that we're going to do. X equals, and by the way, I write my system, my equations side by side for substitution. So for graphing, I write them side by side because I know there's work underneath each one of them I need to do. For substitution, I write them side by side. For the final method that we'll go over in just a little bit, I keep them in a vertical format, one on top of the other, and you'll understand why in just a minute. Okay? So x equals 3y plus 7 is my first equation, and 5x plus 2y equals 1 is my second equation. So what you want to do is you want to take either the first equation or the second equation and find a way to substitute it in to the other one. Okay? So I either want to take this equation and put it into this one, or this one and put it into this one. Now, your choice is, you need to make an educated choice. Okay? So you need to look at what you're dealing with. In order to substitute in for something, they have to be equal. Well, right here, this tells me x is equal to 3y plus 7. This equation is solved for x, and I know what x is equivalent to. So I should be able to take what x is equivalent to and put it into the second equation where I see the x. When I do that, I get 5 times what x is in terms of y, 3y plus 7, plus 2y equals 1. I just took an equation that had 2 variables in it, and I have managed to get only y's in it. And you've been solving single variable equations forever. Okay? So now this is going to be pretty easy. So I need to distribute the 5 to everything that x is, because this says 5 times x, but x was this stuff over here. So it'll be 15y plus 35 plus 2y equals 1. Add your like terms. 15y plus 2y is 17y. Bring down your plus 35, and your equals 1. We're going to subtract 35 from both sides to isolate the term that has the y in it. And then I'm going to divide both sides by the coefficient of y, which is 17. And I have now found y, a number that is equivalent to y. At this point, you're halfway there. You're actually more than halfway there, because this is a lot of work and this won't be near as much. You're going to take what y is and you're going to put it into the first equation where you see the y. So it will be x equals 3 times negative 2 plus 7. 3 times negative 2 is negative 6 plus 7, so that equals 1. Your ordered pair is 1, negative 2. Notice how I wrote my answer still in ordered pair form. If I were to graph those two lines, that's where they would intersect each other. Substitution is really easy when one of the equations is already solved for one of the variables. That makes it easy to start with substitution. Sometimes it won't be like that, and you will have to solve one of the equations for one of the variables. Go for the one that's the easiest to isolate. So you're looking for one that has a 1 or a negative 1 as its coefficient. So, like, I wouldn't want to solve this equation for x because it has a 5 as its coefficient, which means eventually I'm going to have to divide everything by 5. And those numbers don't look like they're divisible by 5. Okay? So you would try to go for the one that had a 1 on it. I'll show you one of those now. 2x plus y equals 1, and 4x plus 3y equals 1. So you can see that neither one of these equations is already solved for one of the variables. So your next question is, well, is one of these variables easy to isolate? So I notice that this y has a 1 as its coefficient. So that's the one I want to go after. An understood 1 is sitting there, right? So how would I solve this equation for y? Subtract 2x. Very good. And I get positive y equals negative 2x plus 1. I'm going to take that and I'm going to put this in for y into the second equation. I get 4x plus 3 times what y is, which has to be put in parentheses so that you distribute it correctly. Then I will distribute the 3. So positive 3 times negative 2x is negative 6x. Positive 3 times positive 1 is positive 3 equals 1. I haven't made any mistakes, I don't think, have I? These are not worked out for me. So you always have to be extra careful with the distributing. You know, you just got to be very conscientious of it. So you make sure you do it to both terms and you watch those signs and stuff. 4x minus 6x is negative 2x. Subtract 3 from both sides. And then divide by the coefficient of x. X equals positive 1. So I found the y coordinate, haven't I? Excuse me, I found the x coordinate, haven't I? The x coordinate, not the y coordinate. I put it in the right spot. Now what do I do with this? You substitute it in. And I like to go back to this one because I'm looking for y. So I've already solved this equation for y, so I'll just use that one there. Y equals negative 2 times x is 1 plus 1. Y equals negative 2 plus 1, so y equals negative 1. So your ordered pair is positive 1, negative 1. Any questions? What's it going to look like if the system has no solution algebraically? That's our next thought, okay? So if the system has no solution, we know what it looks like graphically. They're parallel lines, right? But what would it look like algebraically? So let's explore. Solve by substitution. X minus 3y equals 2. And 2x equals 6y plus 8. Okay, solve by substitution. I have a couple options here. This one is almost solved for x, isn't it? It's kind of weird how they've got that one. I could divide everything by 2, and that one would be solved for x, wouldn't it? Okay? Or I could add 3y on this one, and this one would be solved for x. So you may be wondering, well, how do I know? It doesn't matter. You choose. Whichever one smacks you in the face first and says it's good, do it. Because it's a system. They work together. You're going to get the same solution no matter which one you start with. Okay? I'm going to do this one because the x is almost by itself, and I just feel kind of, pulled toward this one. Make sure you divide everything by 2. So x equals 3y plus 4. So I would take this and I would substitute it in for x here. So I would get 3y plus 4. You could put it in parentheses if you wanted to. You don't really need to because you don't have anything that you have to multiply by it, so there's no distributing to go on. You could just write 3y plus 4. Bring down the minus 3y equals 2. Add your like terms. Positive 3y and negative 3y, they go away. You're left with 4 equals 2. There are some of my students probably who think 4 equals 2, but it really doesn't, not in here. It doesn't. Never on any planet does 4 equal 2. So what I mean when I say never on any planet, not in any universe, does 4 equal 2, it's a false statement. If you get a false statement, there's no solution. Now, that doesn't mean if you get x equals 0. That is a solution. That means x is 0. For some reason, after you show students this, they immediately freak out when they get 0, and they think 0 can't be a solution. That's not the case. I know it doesn't have anything to do with this, but it happens. They kind of transpose it into that for some reason. This is when all of the variables cancel out. You are left with a number equals another number, and they're not the same number. Okay? So no solution, empty set, whatever they want you to write it as. Now, I want you to use your logical reasoning skills. If a false statement means that the 2 lines are parallel and they have no solution, what do you think your algebraic answer will look like if they're the same line and have infinitely many solutions? Using your logic, huh?
2 equals 2.
Sure. You're going to get a true statement. Like what Ronnie said, 2 equals 2. If you get a true statement, that means they're coinciding lines. They're the same line, and they share all their points. That any point you picked would work. Okay? So we'll do one like that just so you can see it. We'll even do one with fractions in it because they're probably going to throw 1 or 2 of those at you. We learned Monday night, I believe, how to solve an equation with fractions in it. What did we say we wanted to do? Who remembers? What? Find the least common denominator with it. Multiply it. It clears the equation of the fractions. Okay, so that is so important when you're looking at an equation that has fractions in it, because this is painful to look at. And truly, I don't want to use any of this to try to substitute over here, or vice versa. It's just going to be hard. And you can make your life easier in algebra if you just think a little bit. So the least common denominator would be 12. Does everybody agree with that? So I'm going to multiply by 12 over 1, every term by 12 over 1. And so 6 will go into 12 2 times. I'm only doing this to make it where it's easy to figure out how to substitute. Okay? So I get 2x, 12's cancel here, minus 1y equals 2 goes into 12 6 times. 6 times. Now, at this point, you should realize, wait a minute, this, which is that equation, just in a manipulated form, and this equation are the same, right? Therefore, these have infinitely many solutions. You don't want to say all real numbers because it's not numbers, it's ordered pairs. It is numbers inside the ordered pairs, but you know it's not just a number. So we're going to say infinitely many solutions. Now, I did want to show you what it would look like if you substituted one into the other. So let's say they didn't turn out looking just exactly alike and you didn't see it right off the bat. So if we took this a little further and we said, let's solve this equation for y. So I'm going to subtract 2x from both sides. Now you got to divide by the coefficient of y, and it's a negative 1 here. So I'm going to divide everything by negative 1, and I get y equals positive 2x minus 6. Then I'm going to take that, and I'm going to put it into this equation where I see the y. I'm going to come down, well, let's see. I could probably squeeze it in here. 2x minus y, which is 2x minus 6, equals 6. You distribute the negative. 2x minus 2x plus 6 equals 6. Your variables will cancel out again, but like Ronnie said, you get a true statement. 6 does equal 6 everywhere, right? So, it's a true statement. No variables involved in it, just numbers. It's infinitely many solutions. Any questions?
So how do we show that?
Oh, the answer? Okay. Let me see if they show me on here again. Yeah. All right, so you say, well, I'm not for sure now. I think if I remember seeing right last semester, there were some of the problems that made you type it in this weird format, and some of the problems that had it already pre-typed for you and you just had to do a little part of it, okay? They may let you choose. It may be like a multiple choice option where you can choose infinitely many or no solution. I know I saw that on some of them last semester, but this is the way you write it. The set of all ordered pairs x, y such that is a big tall line. Stands for the word such that. And then you just put one of the equations from the system, whichever one you want to. 2x minus y equals 6, and you close the set. Okay? So that's one of those nitpicky things that the computer may get you on. But, you know, if you were doing just paperwork, I would know when you wrote infinitely many. But, okay. And it's in your book. You'll see it in there as well in several problems. All right, so I'm going to